I'm going to make a guess about you. Yes, you. I don't know you, but I know one very important thing: you're reading this page. I'll go one step further with my guess: you're reading this page on a computer, perhaps a phone, tablet, or laptop, but some kind of computer. Now, you're reading this page in English. I suppose I just made another guess about you. And this page is composed of select letters within the 26-letter alphabet. Those 26 letters are mixed together by predetermined rules to form more complex words. Now, like I said, you're reading these English letters on a computer. Your computer is a complex machine developed by many smart people over a few years. Certainly, 26 letters wouldn't be an issue for such an innovation? Well, it is. Computer language is very much different than our own, because, while we use 26 letters, computers use just 2 numbers. That's right, computers communicate only using 0 and 1. Read this sentence in English. Simple, right? This is how your computer sees that same sentence: 010100100, 011000101, 0110001, 011000100, 0010000, 011100100, 011010000, 011010001, 0111011, 0010000, 0111011, 011000101, 0110111, 011101100, 011000101, 011011110, 0110011, 011000101, 011000001, 011011110, 0110000, 010000101, 011011110, 0110011, 0110110, 011010001, 0111001, 0111011, 011010000, 0010110. That 5-word sentence easily becomes nearly impossible to read. Every 8-number section of the above sentence, 0101010, is a new letter. How can computers communicate, work, calculate, and function with such gibberish? Well, to tell that story, we'll need to visit the 17th century. A German mathematician by the name of Gottfried Wilhelm Leibniz developed a 2-base number system in 1679, binary system. He published his findings in 1703 in his article titled Explanation of Binary Arithmetic, which uses only characters 0 and 1, with remarks about its utility and the meaning it gives to the ancient Chinese figures of Fuxi, Garfinkel and Grunspan 32. Try saying that title 10 times fast. Our standard numbering system is base 10, meaning we use 10 numbers 0 to 9. These numbers form the base of every other number. But Gottfried developed an entirely new numbering system. His was base 2, meaning he used 2 numbers 0 to 1. With these 2 numbers, all other numbers were created and represented. With his new system, Gottfried avoided nearly all multiplication tables, see they aren't that important, and created simple rules for calculation, Garfinkel and Grunspan 32. His numbering system was called binary, because it used 2 numbers. Let's review a few simple problems and discover how the numbering system works. Each number is represented by a combination of zeros and ones. Of course 0 is represented by 0 and 1 is represented by 1. For larger numbers, we run into some complications, but let's review how base 2 works. Base 2 starts at 0, then doubles every number after that, therefore it could be written in this way: 0, 2, 4, 8, 16, 32, 64, 128, etc. Or written another way: 20, 21, 22, 23, 24, 25, 26, 27. As you can see, the base remains 2, and the power that each 2 is raised increases by 1, doubling each number. This forms the foundation of the binary numbering system. Now let's explore how to represent a number in binary. Whenever I convert base 10, or decimal numbers, to binary, I like to start with a quick table. This makes the process easy and quick on paper. Write out a table as follows. Now let's convert the number 55 into binary. We will start by finding the largest number that can be subtracted from 55 in the table. That number is 32. So we'll place a 1 in the box under 32. 55 minus 32 equals 23. Now we do the process again. 23 minus 16 equals 7. We'll place a 1 underneath 16. 8 doesn't fit into 7, so we'll enter a 0 under the 8. 7 minus 4 equals 3. We'll place a 1 under 4. 3 minus 2 equals 1, place a 1 under the 2. And since 1 minus 1 equals 0, we'll place a 1 under the 1 and zeros everywhere else, and we're done. Our binary number is 00110111, which is equal to 55. To convert the number back to 55, simply reverse the process. Fill the table in with the binary number and add all the places where there is a 1. Therefore, 1 plus 2 plus 4 plus 16 plus 32 equals 55. Now, let's consider a simple math problem using binary. Math with binary numbers is even easier than decimal or base 10 numbers. Let's add 55 to 10. 10 is 00001010 and 55 is 00110111. Our problem is 00110111 plus 00001010. It's the same as regular addition, but remember, you only get to use zeros and ones. Now let's add. Start from the right. 1 plus 0 equals 1. We've hit a snag. I encountered 1 plus 1, which is 2 in decimal, but we can't use 2, but we can use 2 in binary, which is 10. So add and carry, write 0 underneath and carry the 1. We'll continue that same process and solve the problem. So, our answer is 01000001. We can check our answer by plugging into our table. Now, we add the columns which have 1s. So, 64 plus 1 equals 65. We know that 55 plus 10 equals 65. So our answer is correct. Subtraction is carried out in the same way, just reverse. Division and multiplication are done in the same way as regular numbers as well. So that's binary in a nutshell. But why is it so important, and why is binary the only language of computers? Well, at their core, computers control electricity. When you send an email, the computer is only sending pulses of electricity. Really, computers are simply switches that control electricity. We'll explore this concept more in future blogs, so be sure to follow me here on Medium. Now think about a light switch. When you turn the switch to on, electricity flows to the bulb and the light comes on.
When you switch it to off, electricity stops flowing and the bulb turns off.
That's how a computer works. But a computer is made of billions of tiny, microscopic transistors. Each transistor is a switch. When you turn on your light, there are two options, on and off. There is nothing in the middle or onish or offish positions. It's on or off. The same is true for transistors. They are either on or off, nothing in between. In binary, 1 represents on and 0 represents off. So, when we see the binary number 00110111, the computer turns transistors off, off, on, off, on, on. Now, this may seem confusing. You can't turn a switch off, that's already off. But computers work in cycles, so each cycle could be on or off. When we see off, off, the transistor is off for 2 cycles, sending no pulse of electricity, then on for 2 cycles, send 1 pulse for each cycle, etc. Computers use the on and off nature of transistors represented through binary for everything. Every number, letter, shape, and even color on your screen has a binary translation. This is simple to understand with numbers, but how does binary represent this vast collection of information, including letters? During the early days of modern computing, less than 100 years ago, when researchers wanted to build computers for more than calculation, computer scientists discovered this issue. They developed a system of codes to represent all information in the form of binary numbers. One such method that isn't as popular today is ASCII, which stands for American Standard Code for Information Interchange. The ASCII table lists letters, uppercase and lowercase, numbers, and some symbols, with number codes that can be converted into binary. For example, capital letter A is ASCII code 65, which converts to 01000001 in binary. Each letter is 8 digits long. Let's look at a quick example of the word hello. H is 72 in the ASCII table, or 01001000 in binary. E is 69, or 01000101. L is 76 or 0100100. O is 79 or 010011111. So, the word hello is 0100100, 010000101, 010011100, 010011100, 010011111 in binary. Of course, we humans don't use binary. That's where the computer's operating systems, such as Windows, and programming languages, such as Java, are used. The computer converts the information into binary by itself in a process called compiling. In binary we call each digit a bit, binary digit. And each grouping of 8 bits is called a byte. These bits and bytes are the primary measurements for the storage systems of a computer. I'm sure you've heard of a gigabyte when using a USB stick or maybe an external hard drive or when you bought a laptop. 1 gigabyte is about 1 billion bytes and about 8 billion bits. In 1703, when Gottfried Leibniz published his article on binary arithmetic, he could never have dreamed of its use. But binary has become the language of our world, even if none of us ever use it, see it, or speak it. Binaries, zeros and ones power many of our homes, RTVs, smart watches, phones, computers, cars, and much, much more. Binary arithmetic is the 9th major milestone in the history of computing.